Hey everyone! This is going to be a lecture covering two chapters at once, so there's going to be a lot of new vocabulary coming in. Don't panic. I know this is just week two. Why are we jumping in so deep? It's not deep. We're just got to make sure we know the language we'll be using throughout the rest of the semester. We won't be doing two chapters again in 1 week throughout the rest of the semester, so it's just this week. We're getting the hard work done now, so you don't have to worry about it later. And also, I have found that the better you use this language and the faster you use this language, the easier the rest of the semester tends to be. So, we're going to zoom on for this lecture. I'm going to zoom in on what the language and the terms mean, and the textbook and the homework will guide you through how to do those terms, and it'll make a bit more sense as we go on. So the statistical groundwork is the name of this lecture. We're going to look at what is data and how to organize it so it actually makes sense and it's not just a whole bunch of numbers flying at people's faces. All right, let's get going. All right, so for this chapter, here are a long list of terms that we're going to go through. So you'll see that in the middle, I have a list of terms. Those are like larger categories. And then on the right, we're going to have more specific terms. And we even have more terms than are listed here. You'll see them as we get going. Frequency is going to be just talking about exactly that, how often something happens and how do you show people how often something happens or how many people surveyed yes or no on this question. So frequency and showing frequency has a lot of graphs, and we'll be getting into the differences between a bar graph and a histogram soon. Skew and kurtosis, so the second one and the bottom one, those are dealing with graphs also, and how that graph might look different depending on how people respond. Right, so you might have a survey question, where a lot of people answer really highly. That would be a skew, and we're going to look at what that means. And then kurtosis is talking about averages with that graph, and we're going to get to that in a bit too. I do want to slow down on this word population. Population. So whenever we're surveying or doing statistical work on something, we're usually trying to answer a question about a whole population, right? Um, if we're at like Amazon, what time of day do people prefer their lunch break, right? Do they prefer at 11 a.m. or 1 p.m. or early or late or something like that? And the population in that situation would be people who work at Amazon, all the people who work at Amazon. Now, if it's your job to research that question, you just won't have the time and the resources to research every single participant in Amazon's warehouses. So, because of that, the population might not be something you can attain for research, but you can pull a sample, right? A sample is some of the people in the population that then represent the whole thing, right? So I might not be able to get every employee from every warehouse across the entirety of the world where Amazon has warehouses, but I can pull a small sample from each warehouse across large sections. So I don't need every warehouse in Kentucky. I just need like 10 or so people from half of the warehouses in Kentucky to give me some answers. And that will be that sample will represent the population. Now there's another word here, outlier. Outlier are people who answer so wildly high or so wildly low or so wildly different from everybody else that they don't actually help with understanding the research. And what do you do with an outlier? How do they mess with your statistics and things like that? We'll get into more in a bit. And the final thing we're going to talk about is averages, right? When someone says, "Oh, I don't know, just an average number," well, actually, there's three major ways to find out an average number, and they can give you very different stories. So we're going to zoom in on averages. We're going to zoom in on frequency, skew, kurtosis. We're going to figure out how graphs can help us tell a tale, tell a story, and understand what data really means. All right, first things first, let's start looking at graphs. Everyone likes to look at graphs. We're not going to cover all the graphs that could be, we just don't have the time. But we're going to look at some really common graphs first. There are dozens and dozens and hundreds of graphs besides what we're going to be talking about here. And if we take more stats courses in the future, you'll undoubtedly use different graphs in the future. But we're going to zoom in on the bar graph and the histogram for the purposes of this course. And just so we can get our minds around what the purpose of a graph is and how we can look at and understand graphs. So I have two graphs here for you that I just kind of pulled from different stock images on PowerPoint, but they get my point across quite well. So on the left, the left, the bar graph, nominal data, different variables with different values. What does all that mean? So if you'll remember from last chapter, nominal data is data that's just the name. It's just the name of something. It doesn't give you any more information about what's going on. It's just data that helps you organize stuff by name. It doesn't tell you if it's more or less than because it's just a name. And if you look at the ice cream preferences graph, at the bottom, you'll see chocolate, strawberry, horchata, and lime. These are different ice cream flavors. Horchata is not necessarily more or less ice cream than lime ice cream. And chocolate is not more or less ice cream than strawberry ice cream. That's not how we compare those data points. They're just names. They're just categories of ice cream, right? So that's nominal data. And bar graphs do well with nominal data because then on the left side, you can see how many people responded with that is their favorite, right? 0, 1, 2, 3, 4, 5, 6, 7. So if we follow those numbers and the line that draws across the graph, we can look at the chocolate bar, go all the way up, and you can see that the top of the chocolate bar hits number 5. Well, what does that mean? Number 5 means that's 5 people responding saying ice cream is their chocolate ice cream is their favorite. So and that number of people, how do I know it's that number of people? At the bottom of ice cream preferences, there's this little legend or this key that gives me an idea of what that color means. So does that mean chocolate's everyone's favorite? Does that mean chocolate's the best one? No, that just means 5 people liked it the most out of these 4 options, right? Does that mean horchata is the best ice cream that ever will be in some people's mind? Absolutely. In 6 people's minds, horchata will be the best ice cream ever. But since this is nominal data, that's all we can know, is that those 6 people preferred horchata, and that's it. Based on these kind of bar graphs, it actually tells you very little about the statistical whereabouts of what's going on in the story. All we know from this is that lime is least liked, horchata is most liked, and chocolate and strawberry is very similar to each other. But histograms are a different thing altogether, right? So on bar graphs, each bar meant a different category, right? But histograms are different. Histograms only have one variable. Well, they only have one data point. And each of those bars is actually a clump of answers. What does that mean? Well, here you can see interval data, right? So interval data means data that can go up and down at equal intervals, right? So if I say time, 1 second to 2 seconds to 3 seconds, there is only 1 second of difference between each of those. So the intervals are the same all the way up. So if someone runs a race and gets a 15-second sprint, and someone else runs a race and comes in with a 13-second sprint, that means the 13-second sprint was 2 intervals, 2 seconds faster than the other one, and that's a steady set of intervals all the way down to 0 and all the way up to however long it takes someone to run a race. Interval data and ratio data are very similar in this way. So with a histogram, we're only looking at one variable, right? With a bar graph, we looked at kind of 4 categories. With a histogram, we're looking at one category. So let's look at this histogram on the right side, years in current position. For the purposes of this lecture, years in current position means years in this job, at this employer, right? So then, at the bottom, we have 1 to 5, 5 to 9, 9 to 13, 13 to 17, and so on and so on. What does that mean? These are bins. 1 to 5 is 1 to 5 years. 5 to 9 is 5 to 9 years. 9 to 13 is 9 to 13 years. Does that make sense? So we're, instead of reporting how many years people have, each individual person has, that can be very messy very quickly. What we do is we clump all the people together who answered 1 to 5 years, and then we measure the frequency of how often that happened, right? And on this bar graph, on this histogram, we can see 5 people answered that they have been in this job for 1 to 5 years. That means that could be 1 person with 1 year of experience and 4 people with 5 years of experience. We don't know. We just know that they all fit inside that bin, that segment, that clump. The word bin is the statistical word we use for histograms, but if that's too much all at once, you can use clump as a placeholder until you remember the word bin. So the 1 to 5 years bin has 5 people in it, because I look at the top of that and it goes across that line to the number 5, and that's 5 people. And then I go to the next bin, the next clump, 5 to 9 years. 5 to 9 years. Well, if I follow that one to the top and I look at the number that it's as high as, it looks like 10, but just over 10. So there's just over 10 people who fit in the 5 to 9 category. Again, we don't know if that's 1 person with 5 years experience and more than 9 people with 9 years experience, or if there's an equal distribution. We just know that in that category there's a slightly more than 10 people, right? And then we jump really high. The next one up is 9 to 13 years, and that is more than 20 people. And 13 to 17 years, there's more than 20 people there. So these bins, these clumps of years, actually hold lots of responses all at once, right? It's not like the bar graph where 5 people reported chocolate. Done, right? No, it's a bit more complicated than that, right? We have 5 people who reported somewhere between 1 and 5 years. And that's because there's different kinds of data showing up. So that's the bar graph versus the histogram. Bar graphs, nominal data, you can show different, multiple kinds of categories. With the histogram, you're dealing with one category that is split up into its intervals. All right, so for this slide, I just want you guys to look at some more graphs and look at what happens when graphs are no longer symmetrical. We're just going to be talking about the shape of the graph with the word skew. Skew here, we've used the word skew in a lot of American language, sometimes to say we're skewing towards something. And that's not very helpful language. So go ahead, if you need to take a moment and delete the word skew out of your mind, go ahead and do that. We're going to zoom in on what skew means statistically. Skew is mostly used for histograms. and it's used to describe the shape of the histogram. So if we zoom in on this uh, blue graph in the middle of your PowerPoint, you'll see that it says left skewed, which means there's a lot of people who answered over here, but because there's a few people who answered over here, it shifted the average, or it shifted the mean, it shifted it left, down away from the middle where most people are. Most people are over here. You can probably assume the middle is actually supposed to be over here, but because there's some skew to the left, the middle is now actually way over here where there's not a lot of people answering at all. And then on the right side, we have this green graph. And yep, you guessed it, this is the right skew because there's a lot of people who answered on this side. So the middle should kind of be over here. But because there's this one person who answered way over here, the middle is now skewed to the right. So it's a right skew, or like the language that the slide uses here, right tail. The right tail is flatter. So because the right tail is flatter, it's a right skew. Left tail is flatter, left skew. If everything's about flat, it's called symmetrical. But over here on this graph, this is a graph that's only designed to help you understand the different labels and parts of a graph. So don't worry if you don't understand it. It's not actually measuring anything. You'll see here that there's a dip on the right side and a dip on the left. A dip on the right and a dip on the left. This is still pretty symmetrical too. You'll notice that the middle, the highest peak, is actually not dead center of the graph. So there is still technically a skew here. Still technically a skew here. Now look at the tails, look at the green bars, and you can see that this left side has a longer, flatter tail than the right. So this is actually still a left skewed histogram, even though it's a lot more symmetrical in the middle. And say these green bars were slightly different. Say the tail on the left and the right were actually pretty much the same, but there's still this peak in the middle. What is that called? Well, that's actually still symmetrical. Symmetrical in statistics is the same as symmetrical as when you were a kid. If you can fold it in half and it's about the same on each half, then it's symmetrical. So even if you have a really high, sharp point, and then it drops real suddenly, and then there's these long tails that go on forever. Well, if they're about the same on each side, it's still symmetrical. Well, what if there's a long, flat curve, like peak, and then it just barely tips off at the ends each side? Well, if it's even on each half, then it's still symmetrical. There's no skew. Skew is talking about when the tail on one side is flatter or longer than the tail on the other side. Let's talk a little bit more about this left side graph. You can see that there's a mean, median, and mode. And you can see that there's these green bars with this red line. So the red line is giving you like a general shape of averages. And the green bars are telling you exactly how many people or answers there were in each bin, right? And down here, the bins look a little differently. Instead of the bin saying 10 to 11, it says this mark right here is 10.94. So you can assume that the bar between 10.94 and 11.93, that's all the answers between 10.93 and 11.92. So it's still a bin, except the ranges are displayed differently with tick marks instead of like a number to a number. But it is still a bin because we're grouping how many answers can lay in between. It looks like since they're using decimals, there's quite a lot of answers that could be in between 10.94 and 11.93. So theoretically, maybe almost 100 different answers. So you just heard me talk about averages a few times on that last slide. Well, what does average mean? Well, that's a good question, right? There's three major ways to measure how central data can be, and there's three major ways to measure how varied data can be, right? So when someone says average, they typically mean the middle-ist option, right? If someone says, "Oh, I'm an average like writer," what they mean is they're not amazing and they're not bad, they're in the middle. So average means middle-ish. But how do you calculate that statistically? What does that mean statistically? Well, we're going to get into that. And variance, well, variance is how much data varies or how much it changes from answer to answer across the whole board. Well, we measure that with three different ways as well. So mean, median, mode, those are your three major categories for measuring the central tendency or the average. And then there's this one option we're going to talk about very briefly, weighted average. You won't need it too much in this class. And then when it comes to variance, how much your data changes from one ultimate end to the other ultimate end, we have variance, standard deviation, and range. So let's get into it. So let's talk about measuring the average, measuring the central tendency, right? Three major ways to do that: mean, median, mode. You may have heard these before. And that's going to help you a lot if you've heard these things before, but just in case you haven't or if it's been a long time, we're going to slow down and make sure we understand these three words very, very well, and how important that you understand that these are different ways to measure the average and they're not the same. So the mean is what happens when you take all of the answers and you sum them all up, you add them all up, and then you divide them into equal parts again. And you divide them into equal parts. You can think of this as like just taking everyone's cup of juice and pouring it into one big jug, and then taking from the jug and pouring equal amounts of juice back into everyone's cup. So that's what mean is. You sum everything up, you add it all up, and then you divide it back out neatly. You're going to get some practice with this by hand later on in this chapter. I strongly encourage that whenever you have a video that says how to do this by hand, please, please, please get a pad and a piece of paper and a pen and do it by hand with them. It helps your brain understand this math a lot easier. So what does that look like for our data points down here? Well, down here I have completely fake made up information, by the way. Completely fake made up information. I have 27 answers that were given in a survey, a fake survey that never happened. How much annual money does your household make in this county of Kentucky? Whatever county you want to imagine. So I sent out this survey, not really. I sent out this survey that asked the question, how much money does your household make in a year? And these are the answers I got. I got 27 answers. So to find out the mean, the mean average of all of these annual incomes in Kentucky, I would add 21 to 23, 23 to 23, 29 to 29. I'm going to add all of them up. One big sum. And then I'm going to divide that big number by 27 because that's how many people responded to the survey. I have 27 points of data, so I'm going to sum it up and divide by 27. And when I do that, this is the answer I get. This is my average income for that county of Kentucky, right? $96,000. That's really fair. It is statistically The most fair, the most middle, the most numerically middle you will ever get is the mean. And we will use the mean for most of our statistical analysis from here on to the end of the semester. But that's not the only way to understand data. And it's really important that you know that. Mean is probably the most statistically important, but it's not the only way to understand data. So now we have median. Median. Well, what's median? Median is literally the middlemost point, right? So the way I would figure out median is I would count from the left and from the right, and I would get to the middle-ish area, wherever the middle number is, on 27 points of data. So that means I'm probably going to find a spot that has 13 numbers that way and 13 numbers that way, and my middle number will be in between those two 13 numbers. Why 13? Well, 13 plus 13 equals 26. And right in the middle of 26 is my 27th number. Median is literally the middle number. Now, median only works if you've organized your data. I have already set up this data from lowest to highest, but that's not normally how data is collected, right? You might get answers here and from 41,000 to 23,000 to 99,000. So you have to spend time organizing your data first, and then you can calculate the median. I've already done the setting up, so we just got to count from the left side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, plus 1. So this is my middle number because I know there's 13 to the left and 13 to the right. This is my middle number, and the answer is 41,000. Sure enough, median 41,000. Now look at these two numbers. They're already incredibly different, right? 96,000 is the statistical average, but it's not the middle. The middle is 41,000. Well, let's see if we can find any more information out about the average. What's the middlemost point when it comes to annual incomes in Kentucky? Again, fake data. Well, there's the mode. We've checked out the mean, we've checked out the median, now we have the mode. Mode is literally the most frequent point of data. How often does this point of data happen over and over and over and over and over again? So the most frequent point of data is 45,000, right? So to get that number, I'd count, well, how many 21,000s do I have? I just have the one, so it's not that one. I have two 23s, but there's only two of them. Let's keep going and see if we find anything else. Well, here's three 31,000s. 31,000, 31,000, 31,000. That's three of them. So that happened more than 23,000, but that might not be the most frequent one. So you look at all of your answers and you find out which one happened the most. And it looks like 45,000 happened the most. 1, 2, 3, 4, 5 people responded with 45,000 is how much they make in a year. So our mean, median, and mode are three different answers entirely. And if a politician needs to look at taxes or setting up taxes for the upcoming year, they might calculate, well, it looks like the mean or the average household income is 96,000. I think I can increase the taxes this year and everyone will be okay. But then that should make you go, whoa, whoa, whoa. The median and mode are both in the 40,000s. That's very different than 96,000. So this is why we have multiple ways of looking at the average, is because just having one average doesn't always give you the fullest picture of what's really happening, which is another reason we also have graphs. Oh, I love graphs. So, real quick, I want you guys to look at these numbers at the bottom, 23 to 33,000, 33,000 to 43,000. These are bins. So what does that make this graph? Is it a bar graph or a histogram? I know I'm going to get quiet, but you should really try and answer it yourself first. Histogram. Histogram. So if you said bar graph, that's okay. It has bars on it. It's an easy mistake to make. But it is a histogram because we're only looking at one variable, income. And income is not nominal data, it's interval data, right? Because money moves up and down with the same amount of interval all the way up. And these bins are a dead giveaway, these ranges at the bottom are a dead giveaway that it's a histogram, right? So we know that 23,000 to 33,000 happened about 6 times. 6 people responded within that bracket. And 8 people responded within this bracket. And then no one responded in this bracket or this bracket. And then 3 people responded with, I make a lot of money, right? So, if you remember at the beginning of this lecture, I said something about sample and population. Population would be, in this case, in all of the people in the county of Kentucky. Every single person. Well, we can't ask every single person all of their incomes. That would take too long, and it might give us not all the information we need anyway. So we just need a sample. We just need a sample. So in this survey, I asked 27 people from this county. Is that enough? Is it not enough? That's a different question for a different time. But I asked 27 people. That's my sample. Of my sample, most of my answers are down here. And then I have a tail that goes way, way over here. So I have a right skew. I don't have symmetrical data here. I have a right skew. And then way over here, these 3 people who answered, oh, I make a lot of money. And this one who make a lot of money, not as much, but still a lot of money. They kind of messed with the averages, didn't they? Right? And if we look at this data set, 21,000 and then 700,000, this one person, 700,000, does not actually help me understand what's going on in this county. One super rich person does not help me understand what most people are experiencing, because most people are experiencing something very different than that one person. But if I'm calculating mean, I still have to add that 700,000 to the pile and then divide normally. So this is an outlier. They are way off the charts. And because they're an outlier, they're actually messing with my mean. And that's the weakest thing about a mean, is it can change really easily. It can change really easily. The median and mode, those are a lot more stable, but they're not statistically the purest way to find out the average. So that's why we have 3 different ways of doing this. So what do I do? What do I do with this chunk of people who have a very different money experience than the rest of the group? Well, you may not like the answer, but we sometimes just delete their answer. Or we weight the averages differently. There is a statistical formula where I can make all of these averages down here way more, get heavier, if you will, and they help the mean come out a little differently than we're seeing here. So sometimes people have a problem with deleting scores. I understand that. It is still ethically responsible statistical analysis if you can prove that they are indeed outliers and they aren't supposed to be reported in other ways. We're going to talk more about that on the next slide too. So this is how to measure the middle. This is how to measure the average. It's important to know that we have three different kinds because what if you're a politician and you need to make some decisions about your county or your city? Well, you need to know your data really, really well in order to make those decisions. So this is how to understand the middle. Now we're going to try and understand the spread, the variance, or how different the data is from one another. Okay, so we just spent time talking about the average or the central tendency and how to measure that. Now we're going to talk about the variance or how spread out the data is over the whole graph or over the whole range. So we're going to use the same data as before, this 27 points of data from before, except these last three are in parentheses, and I'm going to talk about what that means in a moment. Let's start with some basic terminology. Variance. Variance is how spread out all of the individual data points are, or the individual responses on a survey are, from each other and from the mean. We use the mean for statistical analysis. The median and mode help you understand the whole picture. We use the mean for statistical analysis. So when we talk about variance, we're talking about how spread out things are from the mean, which is why it's really important to have your mean calculated correctly or weighted correctly, or you don't have outliers in the way messing with your mean. So you'll see there I have a note that the variance is related to the standard deviation. So I'm just going to jump right into the standard deviation next. The standard deviation is how spread out a clump of values are from the mean. So you remember in the histogram that we clump values together into bins or into steps, and then there's a number of things that of responses within that chunk, right, within that clump. The standard deviation is less about how many people responded, and it's taking averages from everybody, and it's saying, okay, this is how spread out this clump is, this step away from the mean is, and this is how spread out this step away from the mean is, and it starts doing the clumps for you. It's showing you how the standard or average step away, how big the standard or average step away from the mean is, right? So if I had a very large standard deviation, that means there's a lot of people who take one step away, and there's a lot of people who take an even further step away. But if I have a very small standard deviation, that means that the mean is here, and then people don't really step away from the mean very much at all. Right? So standard deviation is how far is the average step away from the mean. What does that mean mathematically? You'll get into that in the rest of your textbook. The last word I wanted to cover here is range. Range. Range is the total scale of answers and data points from the highest to the lowest, right? So if we look at our data set down here, pull from our population, we pulled a sample. Our range would be 21 to 700,000, 21,000 to 700,000. That's our full range. That's our full lowest point to highest point. So I would just take this 700,000 minus 21,000, which I believe is 679,000 is my total range. 600 is a big one. Oh, here I already did the math. I don't need to do it in my head. 679,000 is the total range. But you'll see here I've got parentheses. What am I doing with these parentheses? Well, I'm deleting these 3 points. They're outliers, so I've deleted them. So I don't have to mess with them. They don't mess with my scores. So 679,000 is the range I would have if I kept my outliers, but I got rid of my outliers. Now my range is 78,000. That tells a much more realistic, more true story to what's happening in this Kentucky county than 679,000. If I'm looking at range and I see a huge range like that, at me as a statistician, I see that range and go, oof, we don't know much of what's going on because there's so much variance. We can't say yes or no or this is happening because a lot is happening. A lot of different things are happening, and nothing's very clear. But a range of 78,000, I'm like, oh, maybe we can work with that. Maybe we can work with that. So let's look at the mean again. One more time. I know we're supposed to be talking about variance, not averages, but I wanted to show you what happens if we delete our outliers. So 96,000 was the mean we had last time, but if I delete those outliers, my mean becomes 42,000. I didn't delete the high scores, right? There's 67,000, there's 84,000, there's 99,000. I still allowed some of these higher scores. I just deleted these that are more than 4 times the highest score. They're in the category all of their own. So because they're in a category all their own, I removed them from the math of averaging out the mean, and now look at the mean. 42,000? That's pretty close to the median in mode. That's much closer. And so close, I might actually trust the mean more than I trust the median in mode. So now that I have a mean, I can talk about variance and standard deviation. I need to have a mean in order to do these because the standard deviation and the variance, they're related to the mean. They're not related to median, they're not related to mode, they're related to the mean, the statistical mathematical average. Mathematic average. So, standard deviation, 17,000. What does that mean? What does that number mean? You'll learn how to calculate standard deviation on your own and later on in this chapter, but I'm here to tell you what it means. So if I see a standard deviation of 17,000, that means the average person makes 42,000. That tells me that. The mean tells me that. The weighted mean tells me that. And then the next clump of scores is 17,000 away from that. So the next clump of scores higher than the mean is probably going to be 59,000, somewhere in the 59,000 zone. And one standard deviation below the mean, one step away from the mean, that's lower, well, that's probably going to be 25,000. 25,000. Does that make sense? I'm using the standard deviation. That's the average step away from the mean. 17,000. That's one step away from the mean. So if the mean is the middle, if I wanted to go higher, the 17,000 is one step higher and one step lower. It's just the step, the size of the step. It's just the size of the step. Variance, right? Or if we look at the parentheses again, if my 159,000 is my average, if I kept those outliers, which doesn't make any sense if I look at my mean. My mean is only 96,000. But one step away from that lower is going to be negative something, negative 60 something. No one makes negative $60,000 a year. That doesn't tell me anything about what's really happening in this Kentucky county. That's why we get rid of our outliers. That's why we get rid of our outliers. And finally, let's look at variance. Variance is a very different kind of score. You'll learn more about it in a bit. 291 seems kind of high, but it is a lot better than 26,000. A lot better than 26,000. So it might feel kind of weird to delete these 3 scores because that's the point of getting statistical knowledge is you use the whole sample, but sometimes what happens in the sample kind of messes with your outcomes, and it's important that you delete them so that you understand what's really happening and you get actually a more realistic sense of what's happening in your population. So we just talked about standard deviations, and I wanted to zoom in on that because if you understand standard deviations well, if you have a strong understanding of standard deviations, statistics gets so much easier. So I wanted to zoom in on that. This is going to be a reference graph. I hope you copy this, draw it yourself, mess with it however you can, because it's an important one to understand. So let's look at this real quick. We have our bar graph, not our bar graph. We have our bell curve, our symmetrical bell curve right here. Most people answer in the middle, in the average zone, and we don't have a lot of people who are answering far low or far high on their scores. What does this mean? So if this was IQ scores, most people have an average IQ, right? That's why it's so high, because that's the point of having the average IQ. There's not a lot of people with a very, very high IQ, and there's not a lot of people with a very, very low IQ. But most of us are here somewhere in the middle. There's some of us that are a little bit higher and some of us that are a little bit lower away from the average, but we are mostly in the average. So what do all of these numbers on this screen mean? Well, let's start with this funny shape here, right here. You see it dead center, and then you see it again with a plus, and then you see a +2 and a +3, or a -2 or a -3. This is the Greek letter for mean. This is the Greek letter for mean. It's the average, it's the middle Greek letter that we use for statistical analysis, the mean. So when you see this over and over, this is the mean plus another letter, another funny shape. This is the Greek letter for standard deviation. So the mean plus 1 standard deviation, this is the mean plus 2 standard deviations, this is the mean plus 3. This is the mean minus 1, minus 2, minus 3. Remember, standard deviations is the size of the step away from the mean. Now, whatever the standard deviation is, whatever that number is, who cares what that number is, who cares what the mean is? If you did your statistical analysis, like you cleaned up your data correctly the first time, you're going to have 34% of your responders and 34% of your responders right here dead center around the mean. You're going to have 68.2% of your responses right here around the mean. That's what these two blue sections mean. That's what this 68.2 means. You're going to have more than half of your responses, your answers are going to be right here in the middle, if you did all of your data cleaning well, which we'll talk more about later. So within one standard deviation higher, one standard deviation lower, you're going to have 68% of your responses right here around the mean. That's what this blue section means. That's what this, we cut it in half because the mean is this singular point, but someone might answer slightly higher, slightly higher, slightly higher, slightly higher within this zone, or someone might answer slightly lower, slightly lower, slightly lower within this zone, but they are both within one standard deviation of the mean, one standard step away from the mean. And that's just always true. I wish it was more complicated, and it is more complicated. It needs more nuance, but not much so for stats, intro level stats. You will always find this magic number, which is why I'm presenting it to you guys. If you understand this graph really well and have it really well, you can understand a lot about data coming up in the future. So that's one standard deviation. Well, what about two standard deviations? Two standard deviations away, right down here, you'll see this 95% of answers will be within two standard deviations. Now, it's not just talking about 13 plus 13, because that's only 26%. No. Within two standard deviations is the pink and the blue. Pink and the blue together. Pink and the blue together. I could zoom in on this section between 1 and 2 standard deviations. That's going to give me 13%. 13% of people are between the first standard deviation and the second standard deviation. But if we're including the first standard deviation and the second standard deviation, both positive and negative, away from the mean, 95% are going to be right there. And then again, between the second standard deviation and the third, this last segment, very, very few responders, very, very few values or data points here, very few. 2.15% on this side, 2.15% on this side, only 4% on if you add those two tails together. But if you add all of them all together all the way, 99% of your scores will be within 3 standard deviations. So if anyone ever says something like, oh, I'm 4 standard deviations away from the mean, you can laugh at them and say that's statistically impossible, because we don't really ever get to 4 standard deviations away from the mean. And if that is true of them, they are truly out of this world. Again, because if we're talking IQ scores, I'm not talking like someone who's really smart, because that's this 1 standard deviation away. If they are really smart, they have moved away from the mean by 1 standard deviation. Now, if they're ridiculously high scoring on the IQ, way past not just average, we're not talking averages anymore, we're talking prodigies, we're talking people that you don't really even meet in a lifetime. There's only a 2% chance that people are scoring that high on the IQ in the first place. 2 to 3 standard deviations away. After 3 standard deviations, man, we're talking about numbers so small it's ridiculous. But this is why we use the mean, because the mean gives us a mathematical number to do all of this shenanigans with. And this might be hard to grasp right now, but what I really want you to take away is standard deviation means this size of a step away from the mean. 34% of people will respond within this step away from the mean. 13% of people should respond within this step away from the mean. And that's all calculated in the rest of your textbook coming up. So please take time, understand this, send me emails if you don't understand this. We can set up some meetings. But this is very helpful for the rest of our statistical course. When we start analyzing average versus average, we're going to come back to this. So please have this down before we move on with our course. So the first thing I should be hearing you guys say through this screen is, but Instructor Junker, not every data set is going to look perfectly bell curved. It's not going to have this nice gentle slope, a nice peak, and then a nice gentle slope. And you're absolutely correct. Because of skews and because of kurtosis, we can see lots of graphs will look very differently. These are a couple skewed graphs, and there's a kurtosis problem. So I want to talk to you guys a little bit about kurtosis and a little bit about how to get back to that bell curve that we were just talking about. So right here on this left side graph, you can see that we have some really tall blue columns. Blue columns, bars on a histogram, are real scores. Those are real values from whatever test was given, right? The yellow line is to mark out variance that is calculated by the mean and standard deviations, right? So you can see here that we have a lot of blue jumping over the yellow here, but the middle of this yellow is got a nice dip, and then we have another big jump, and then we have a dip, and then a jump, and then a more dip. So because we have this overall shape going to the right, the tail is kind of going off to the right. We have a skew going off to the right. But it's not just a skew, is it? We have all these hills and valleys. That's a kurtosis problem. Kurtosis is how sharp the peaks are or how flat the peaks are and where those peaks are showing up in the graph. You'll see them in your flashcards coming up later on in this section on Blackboard, that there's 3 prefixes: platy, meso, and leptokurtic. Leptokurtic, mesokurtic, platykurtic. Those are 3 different ways to understand kurtosis. And you'll get a chance at understanding exactly what shapes are happening there. But I just wanted to talk about quickly to point out that it's not just a skew problem, but we have these dead spots as well that create a funky looking shape. And over here on frequency of crayfish and what temperatures they prefer, we have a lot of crayfish right here. But then we have these dead spots. So I'm going to let you in on a statistical secret right off the bat. So you'll see that on the bottom we have preferred temperatures, and then on the left we have frequency of crayfish. If we mess with some of our means, if we use some formulas that are acceptable statistical formulas to transform our data, we apply these formulas to each of these scores, we can actually transform the shape of the graph back into a bell curve. And you don't need to know how to do that. That's not coming up anytime soon. I just wanted to give you guys a little sneak peek into how does this graph eventually become a bell curve? How does this graph eventually become something where standard deviations mean something legitimate? Well, later on in statistical courses and even later on in research courses, you'll learn about transforming data, and that's part of cleaning up. That's part of cleaning up data. Like when people responded to the Kentucky County example earlier, it's not like I'm going to get the lowest score first and the highest score last when people answer these surveys. No, it's going to be jumbled up, right? So I have to clean the data and organize it. But another step of cleaning is looking at this kurtosis and these skews and using other mathematical formulas to clean it up and make it look like that bell curve again. And because we use the same formula on every individual score, it is still statistically accurate. It is still ethical even, and we're not like lying to anybody. And if that's hard to understand, you feel free to email me, and we'll talk more about that later on. But I just wanted to give you guys a quick sneak peek into why that bell curve is so important, even if some of our graphs look wildly different than a bell curve. Well, technically, we can use math to push everything back into a bell curve. And you won't have to worry about that for this course. I just wanted to set your hearts at ease. I hope that you guys have everything you need to get going on the rest of this chapter. Make sure you have these terms down: mean, median, mode, kurtosis, skew, averages, standard deviations, variance. You need all of them. You need all of them for stats. Make sure you have them down pat before moving on. All right. I'll see you guys next time. Email me if you have any questions. Bye.